nonlinear interaction of the ice sheet and the liquid disturbed by a rectangular obstruction on the bottom. The ice sheet is modeled using the Courant theory of hyperelastic shells. The solution for the fluid is fully nonlinear and has been obtained using the integral holograph method by constructing the complex velocity potential of the flow. So we introduced the full number based on the depth of the channel. Complex potential includes velocity potential and the stream function. They both satisfy the Laplace equation in the fluid domain. The boundary conditions can be presented through the stream function. On the bottom, psi is constant and equal to 0. On the interface, the stream function is also constant, but equals to unit. Since we choose the inflow velocity as the reference velocity and the channel depth as the reference length, the dynamic boundary condition assumes that the pressure on the interface is the same as the pressure bending the ice sheet. We use Courant theory of hyperelastic shells, which relates the bending pressure and the curvature and its derivatives of the interface. Helmholtz was the first to introduce a complex variable for solving fluid dynamics problems, and Kirchhoff proposed a conformal mapping technique for solving free streamline flow over a plate. The technique requires finding a conformal mapping of the complex potential plane onto the complex velocity plane. And in order to further develop the conformal mapping technique, Joukowsky and Michel proposed to introduce an auxiliary parameter plane or a zeta plane and search for two functions as the functions of the parameter variable zeta. One is the function omega, it is log of the complex velocity, and another is the complex potential, W, or its derivative, dw d zeta. If these functions are found, then the velocity field is obtained as a function of the parameter variable zeta. The function relating the parameter plane zeta and the physical plane z is obtained as the integral of the ratio between the derivative of the complex potential and the complex velocity as follows. This is called a mapping function. Okay, so the complex potential plane is just a strip. The real potential changes from minus infinity to infinity on the bottom, and percent equals 0. And it changes the same on the interface, and percent equals 1. Because the complex potential plane is very simple, we can easily find a conformal transformation. The function log zeta conformally transforms the first quadrant of the parameter region onto the strip or the complex potential region. Okay, the next great step in the development of the methodology for solving two-dimensional free boundary problems was made by Chuang. He developed a methodology called the method of special points, which allows one to obtain a desired complex function without using any explicit conformal mapping technique. This methodology was applied to derive integral formula, which analytically solves the mixed boundary value problem for a complex function defined in the first quadrant. On the real axis is given argument of the complex function. On the imaginary axis is given magnitude of the complex function. Then the function is obtained as equation 5 shows. Okay, so the argument of the complex velocity is determined by the slope of the obstruction. It is constant on the sides and takes step changes at the corners. The step changes delta gamma at points A, B, D, and E are shown in equation 6. In order to use the integral formula 5, we should evaluate the step changes at points A, B, D, and E. The way how the integral is evaluated is shown in the line of equation 7 for the case of point A. By doing the same with other corner points B, D, and E, we obtain the expression for the complex velocity in the form 8. The mapping function z zeta is obtained in the form 10. Okay, it is seen that equation 10 contains a logarithmic singularity that makes computational difficulties. We introduce the complex potential as a parameter variable and replace data, cosine and eta, by w, phi, and psi as shown in equation 11. Then the complex velocity and the derivative of the mapping function take the form 12 and 14 respectively. Okay, what's next? The complex velocity contains unknowns A, B, D, and E in the parameter plane. They are determined using the length of the horizontal and vertical sides of the rectangle, as shown in equations. Okay, the unknown function of the velocity magnitude is obtained numerically. In discrete form, the velocity on the interface is sought at nodes phi k from -infinity to infinity, and psi equals 1. We calculate the shape of the interface. Then using spline interpolation, we can determine the curvature and its derivatives. Having this, we determine the pressure coefficients for the liquid using Bernoulli equation and the pressure coefficient due to the bending of the elastic sheet. They should be the same. And equating them, we obtain a system of nonlinear equations respect to the velocity's magnitude and the nodes. Okay, so differentiating Bernoulli equation with respect to the arc length coordinate along the interface, and considering both with and without S sheet, we can obtain the dispersion relation as shown in figure 2. You can see for elastic sheet, there exists a critical Froude number, and it depends on the S thickness. Okay, so next part is about the results. And then figure 3 shows the interface shape corresponding to the obstruction height, point 2. We can see that with the Froude number getting closer to critical value, the response of S sheet becomes stronger. The figure 4 shows the interface shape corresponding to the onset of convergence of the subcritical solution. We can see that with the Froude number approaching the critical value, the maximal height of steady solution decreases. Okay, so figure 5 shows the effect of the rectangle height on the interface shape for the number 0.5. We can see that while the height of obstruction increases, the deflection of S sheet becomes larger, and the largest perturbations of the interface appear at the ends of obstruction, then decay rapidly towards the center. Figure 6 shows the onset of convergence of the subcritical solution for different Froude numbers. We can see that with the Froude number approaching the critical value, the maximum height of steady solution decreases. Although in figure 6, the response of blue line is weak, we cannot calculate larger heights. Okay, figure 7 shows the effect of the S thickness on the interface shape for the obstruction height 0.5 and for number 0.5. We can see that with the thickness increasing, the deformation gets smaller, or in other words, the ratio F divided by F critical also decreases, which means the gap between F and F critical is larger. Figure 8 shows the effect of the rectangle length on the onset of convergence for the number F 0.5 and the S thickness 0.003. You can see that generally the maximal height increases while obstruction length gets smaller. And when obstruction length is smaller than wave length, there will only exist a trough on the interface. And when larger, there will be waves decaying towards the center. Figure 9 is the same as figure 8 for the number 0.45 and S thickness 0.002. Okay, so figure 10 shows the effect of the basin length on the onset of convergence of the solution. It provides similar conclusion with the obstruction length, but it is shown that for the length smaller than 2, there will be no limitations on the depth of basin. Okay, about the conclusion part, there this study, a fully nonlinear solution for the steady flexural gravity waves in the channel of polygon-shaped bottom shape is presented. The case study presented the subcritical flow regimes, and the solution is obtained in the form of a system of nonlinear and integral equations, which are solved numerically. It is shown that at some length and height, the steady solutions may not exist. The maximum height gets smaller when for the number approaching the critical value. And the effect of the obstruction length shows that generally the maximum height increases as the length getting smaller, and the largest perturbations of the ice-liquid interface appear at the ends of obstruction, then decay rapidly towards the center. Effect of the basin length on the onset of convergence of solution provides similar conclusion with the obstruction length, but it is shown that for the length smaller than 2 depths of the channel, there will be no limitations on the depth of basin. So this is my presentation. Thank you.
Thanks, Chiang. It is a good presentation, and you gave us plenty of time to discuss and question answer. So is there any question? Any questions? Okay, no question. Liang, in equation 10, you have mentioned about logarithmic singularity. How is that singularity comes? Can you please explain little? Yeah, in equation 10.
Yes, you can see it's you can see that equation yes. So you can see that in equation 10 there is a term d psi or d zeta or theta, and this is
that red colored point.
yes.
Okay.
This is the logarithmic
Okay, it's an integral.
yes.
Yeah, okay. And you go to your figure slide 12. Yeah, so here is it a means rigid barrier, standing barrier at the bottom, or it's a strange means construction with very small width? Which one?
Yes, it is very small length. It is like a stick in the middle.
Okay, but it is means from the figure it is not clearly visible. It is widened or it's just a rigid barrier. Okay.
Yes, it is rigid. Yes. Okay.
Thank you, Liang. So we have
Thank
our
you.
time. Yeah, thank you very much. You can stop your screen share.
Okay. Thank you very much.